Okay, so you are here, which is good because I think after 2 days there is a holiday, right? So many people have left, right? These people are not there, right? Anyway, uh, so normally when this kind of thing is there, I take in normally a quiz, right? So we can look at it, right? At some point. Anyway, so I was covering this basic mathematics, okay? And we were looking at this public key cryptography. And as I mentioned, I have to do some sort of so as you may recall from your discrete math class that we have looked at RSA crypto system briefly. So whenever you log in into any secured website, where there is HTTPS, so there is a strong role of RSA crypto system. We covered a couple of these things earlier, right? And so we were doing this, some basic mathematical thing. Kind of some of these things you already know, and some of these things we are just recalling. So as you know, this algebraic structure, integer modulo n, Zn is a very, very interesting object. And it is a field only if n is a prime number. So in that case, every element, every non-zero element has an inverse, right? And in general, an element B in Zn has an inverse if and only if GCD of B and n is 1, right? So basically, if I ask you to find an inverse of an element, we need an algorithm for finding an inverse of an element in Zn. It is quite useful. And there are certain algorithms which are basically based on, so which is known as extended Euclidean algorithm, EEA, to compute this inverse, which I am going to tell you now explicitly how to find the inverse of an element if it exists. So basically inverse exists as you know, right? If GCD of A, that element in n is 1, only then only the inverse exists. For example, in Z4, 1 and 3 has inverse, right? 1 and 3 are self-invertive. And you can check by making the table. So normally, Zn star in the subsequent lecture is all those numbers A modulo n such that GCD of A and n is 1. For example, in Z4 star, there are two elements, 1 and 3. So these are known as set of units. Units means elements which has inverse. Okay, 1 and 3 in case of Z4 star, right? So set of residues modulo n and relative prime to n, right? Okay. So we were looking at the Secluding algorithm earlier. So in order to find GCD of two numbers, you need to look at these sequence of numbers R0, R1, which are the initial numbers A and B, and then R1, R2, R3, and so on. So basically, we are continuously dividing and looking at the reminders. So for example, R2 is a reminder in the first case, R3 is a reminder in the second case, and so on, right? And QIs are quotient. I mean, this is a very obvious algorithm. So when we compute, we know that GCD of R0, R1 is same thing as GCD of A comma B, which is same thing as Rm, right? In this case, right? So we need to find a way of doing this. So this was the algorithm for finding this GCD, and you will see a little bit modification to this for computing the inverse, which is known as extended Euclidean algorithm. So let us look at some values here. So basically, now we develop this result. If T0, T1, Tm and S0, S1, Sm are numbers, we can define these sequences of numbers Tj and Sj. T0 is okay. T0 is 0. Yes. Can someone tell what is the value of S5 at the back? What is the value of S5? How do you know? Actually, whenever you do one-way flow, right? So human mind is always, not focused much, right? So that's why I'm giving you what is S5. Can you tell me? Just do the calculations and tell me what is S5. So just do it, So you need to find QIs. And how to get QIs? I mean, the previous algorithm, you know what are QIs, right? So QIs are these quotients. In fact, there is this result which I am writing without a proof, that for each j between 0 and m, Rj is equal to Sj R0 plus Tj R1, where Sj and Tj are sequence of numbers given by those expressions, and R0 and R1, you know the initial thing, right? And one can prove it by induction. I am not doing it. I am leaving it as an exercise for you, kind of t time problem, which you can do it, right? Anyway, I'm going to describe now extended equilibrium algorithm. So input is a comma b, and I'm going to compute r, s, and t such that r is the GCD of a and b, and so s and t are numbers such that their linear combination gives you r. So we know this is a very fundamental result in number theory. If GCD of a comma b is r, there exists integral s and t such that s times a plus t times b is equal to r. Now here I invite you to think. Do you think that you can find some new algorithms to actually compute these things? Whatever I am telling you is already known in these books, but do you think you can find a new way to compute these things? Think over it, okay? I may ask this in exam. Now when you say that, okay, अब तो मैं project दे रहा हूँ ना, exam नहीं दूंगा, quiz तो कभी भी हो सकती है, right? So I'm just telling you this, okay? Okay, this we have done anyway last time, right? So if GCD of R0 R1 is 1, there exists R1 inverse, which is Tm actually, right? So because R1 into Tm is equal to 1 mod R0. Okay, in the class now I invite. So this is the algorithm, extended equilibrium algorithm. So we know that the initial values R0 R1 is given here, right? 75 is R0, R1 is 28. I want to find 28 inverse mod 75. It's a very beautiful. Actually, if you can find new algorithms, certainly it will be a very useful thing. Someone in the class tells me how this 9 is coming. Anyone in the class, can you explain how this 9 is coming here? So the starting value is. So what are the, so I is 0, 1, 2, 3, 4. So I'm noting down numbers Ri's, right? Qi is the quotient, and those SITIs as per those expressions, right? Can anyone tell me how this 9 is coming? So we know that R3 is 9. If you look at starting from here, so what we are doing, so initially A0 is A, B0 is B, right? So initialization is there for this algorithm, right? And then quotient is calculated. First time, second time, third time, right? You're just computing the quotient, right? Those QIs are the quotients, right? So basically, you see starting from here, so we know that 28 times 2 is how much? 56, right? And if I subtract from 75, 56, how much is the value? That's the next value, right? Do you know what is happening here? Then again do the same thing, keep on doing the same things. So essentially you are doing the equilibrium algorithm all the time, right? To do these calculations. Finally, I mean, these numbers are important. So basically at each time I am telling you I am going to ask questions. So, maybe I'll give you this table. I'll say that how to compute this 9, or maybe this 9, okay? This 9 here. Okay, so the questions can be created very easily, right? So basically, essentially, when finally you get these numbers 3 and -8, so that means 3 into 75 minus 8 into 28 is nothing but 1. Okay, because these are your S and T, right? So we have this value is 1, modulo 75, this portion will go down, I mean this will be 0, modulo 75, and you are left with minus 8, right? So minus 8 modulo 75 is 67, so you can find the inverse. So essentially, see, whenever you are doing your computing an algorithm, you are making this pseudocode kind of thing, you need to think that what are the, so when you do something by hand, how do you kind of automate, right? Or key features of the algorithm you can separate it out, and you can write it in the form of pseudocode, right? And that is how you do programming. So I hope since you are very good competitive programmers, you know these things, right? Anyway, so this is the algorithm for computing inverse actually in general. This is a little bit fast actually. So you can see that here the sequence SIs are not there, you see, from this algorithm and this algorithm. So I'm asking you same computing. So our task is integer modulo n. B is an element in this. I am asking you invent a new algorithm of your own to compute the inverse. Can you think about it? Even if your algorithm is very weak, that's okay, because essentially we need to ask, once you develop an algorithm, how fast it is, what is the complexity, and so on. These are the questions you can ask as a computer scientist, right? To think about it, finding inverse is a very important problem. Given an element Zn, how do you find an inverse? Okay, B in Zn. This is something very important. Now this is another very interesting result. I think this also you know from your discrete math class, Chinese remainder theorem, right? So if you have equations like, x is congruent to a1 mod m1, x is congruent to a2 mod m2, x is congruent to a3 mod m3, and so on. xr is congruent to ar modulo mr, where mi and ai's are integers and mi's are pairwise relatively prime, means the GCD of mi comma mj is 1. Okay. So then this has a unique solution, capital M is equal to m1 m2 mr, which is given by this quantity. So I think where capital Mi is capital M divided by Mj. Capital M is actually product. Okay. So capital M is product of all these Mi's, M1, M2, Mr. So I leave it because you have done last time. See the calculations. If you put M is equal to these values, you can compute. It's very useful. Chinese remainder theorem is very useful. So whenever we are looking at any structure over, say, Z3, say, or ZP, and you are looking at something in ZQ where P and Q are primes, right? Then you can use Chinese remainder theorem to get some idea about integer modulo P into Q, right? So these kind of things are pretty important, in number theory. Groups. How many of you know group in the class? How many of you know groups? Raise your hand if you know the group. कोई नहीं बोलेगा. Raise your hand. Okay. So answer me this question. How many groups are there of order 4? How many groups are there of order 4? It's a beautiful question, right? And I think I have shown you the flavor already. In your discrete math class also I have shown you, and in this class also I have shown you. So probably you know the answer. How many groups are there of order 4? So what is group? Group is a collection of, so you see, from field you generalize to ring. From ring, when you go to the single operation, you look at only single part of it. For the calculations, you get group, right? The properties are that for every element a comma b in G, a into b is in G, means a closure. A into b or a star b. Star is some operation. It could be addition, multiplication, whatever, right? And for every a, b, c in G, there is an associative law, right? And then there exists the existence of identity element E in G, such that for every A in G, A star E is equal to A is equal to E star A, and for every A in G, there exists inverse, right? Such that A star is equal to A, we also call it, so A star A inverse is equal to A inverse star A is equal to E. For example, integer modulo n is a group with respect to modulo n operation plus n. Group is a very, very fundamental thing. Each of you should know about groups in details. If you have not done a course on group theory, you may have found that this is not needed in your competitive programming, right? So, but you will be at great loss if you don't know about groups, because see, the discovery of groups happened because of solving bunch of system of equations, right, or equations basically. So while solving the equations, the invention of group was there, and it appears at different places in the nature. In geometry, you will find a lot of applications of group theory. In physics, in chemistry, and at many places, So this is a tool which you should know very well, right? And there is one natural book is John B. Fraley, a first course in algebra. I am sure you must have a copy of it. Normally, another popular book which I like is Ian Hustine, Topics in Modern Algebra. If you have done the exercise at the back end, then you will realize the beauty of mathematics, right? And also when you read that book, and there are certain tea time problems, he also leaves, right? So you can enjoy, because he will leave certain portion and he will ask you to do something, okay? So normally, people say that if you want to study algebra, you require a nice, comfortable chair and a cup of coffee to enjoy the beauty, right? So anyway, so this is group. So I ask, like one can form a group also if there is a traffic police person, and suppose there is a car on a crossroad. The turning of car, by just turning of car, and how to start, and if you name the roads like F front, back, B, R right, L left, the turning left right, actually that kind of configuration can also form a group. So I leave it as an exercise for you. If you can show me that it is a group, that means you understand everything about it, right? So you see, again, listen to it carefully. There is a configuration. So basically, when I want to make a group, what I'm going to do, I'm going to make a table. Operation is star. Elements are L, F, R, B. L, F, R, B. L means left, R means right, F means front, B means back. LRFB on this side and LRFB on this on the other side, right? We are making a table. Now, star operation is defined like this. If I am at one of the junctions, so suppose I am at L, means you can assume I'm not writing anything here because I want you to imagine, okay? If everything is shown to you explicitly, you cannot think, right? So now there is a traffic police in the middle. There is a crossroad, and the crossroads are names, right, as I mentioned to you, L, F, R, B. Okay. Now suppose I want to combine L with F. So my car will be at L road facing the police. So every time we start the operation, we assume that the car is facing the policeman at the center. So from left, now I have to combine F. F is front. So now what I mean by front means the car will take that action. So car will go on the front, and the ending should be such that car is again facing the policeman. So that can happen. So this kind of turning is not allowed. You come back with the same, you went like this, you come back like this. So starting from L position, you took front operation. So L combined with F will giving you L itself. So F is acting as an identity element. Got it? So this kind of, arrangement, you can see that F is here, identity element in these configurations. You can make the table LFRB, LFRB, and fill the table, and it forms a group. See, so different ways you can think about groups. A very, very beautiful thing. Anyway, finite group, infinite group, order of an element in a group, the smallest positive integer such that g raised to power m is 1, right? So g keep on doing the operation m times. So how many of you know the Lagranges theorem? Okay, 4, 5, 6, whatever. Rest of the people are busy with competitive coding, right? Anyway, so if G is a group of order n, and I can say that suppose it's a multiplicative group, right? Lagrange's theorem says that order of an element in the group divides the order of the whole group. Okay, whole group is the number of elements in the whole group, right? And this is a very beautiful result. Okay, and actually its corollary is if B is an element is Zn star. Remember Zn star is what? Kind of elements. Like for example in Z4 star the elements are 1 and 3, right? B is an element Zn star, then B raised to power phi of n is congruent to 1 mod n. So what is phi of n? Euler-Toscan function I mentioned to you. So this is a result, and why this will be true? Because Zn star, what is the size of Zn star? Zn star consisting of all elements which has GCD 1 with n. Right, so this is essentially phi of n, Euler-Toscan function. Those many elements will be there, right? So Zn star is a multiplicative group of order phi of n, right? And hence B raised to phi of n will be congruent to 1 mod n. Right? So it's very interesting. So just you know the structure of the groups and so on, you can do many things. Another corollary is the Fermat-Little theorem, right? Suppose P is a prime, B is a member of ZP, then B raised to power P is congruent to B mod P. That means B raised to power P minus 1 is congruent to 1. Obviously, because if n is prime, phi of P is P minus 1. So essentially the same result, right? Because phi of P is P minus 1. I mean, this is something straightforward. Again, if P is a prime number, ZP star is a cyclic group. So that means, you know, if you look at Z3, it's a cyclic, Z3 star is a cyclic group. Z5 star is a cyclic group. So you can just make the table and see. Cyclic group means, you know, you can just, you can find a generator for it, right? So that means there exists a alpha in ZP star such that order of alpha is P minus 1. Because, what is the size of ZP star? P minus 1. Because total size is phi of n. If n is prime, the number of elements, so phi of P is P minus 1. So the number of elements are P minus 1, right? So if the order of, if there exists one element in ZP star just which has order P minus 1, then this will work as a generator, right? For the whole group. In fact, in terms of finite field, we call it as a primitive element. So alpha is a primitive element. So an element is a primitive element if its order is P minus 1. In ZP star I am talking about. Okay? Primitive element. So in that case, if alpha is a primitive element, then ZP star can be written as powers of alpha. And I think you might have seen that at the time of construction of field with 4 number of elements, that alpha that you use in the construction of field is nothing but a primitive element, right? Because that's how everything is written in terms of powers of alpha. That is the observation that you might be remembering. There are a couple of other results. How many primitive elements are there? Number of primitive elements is phi of P minus 1. By the way, it's an interesting thing. You know some of these facts already. Even if you don't know, take a cup of tea and try to verify these things. I will ask these certainly in the exam or the quiz. I'm giving you a challenge. I'm telling you, I'm going to ask these things, right? These are small elements, right? Small things to observe, right? Prove it or verify it or search on Google, whatever way you do. At least spend some time with these things. As an example, you can see that if P is equal to 13, so phi of 13 minus 1 is what? Phi of 12, phi of 12 is 4. So there are 4 primitive elements. So now first check whether 2 is a primitive element or not. So we are raising 2 raised to power 0 is 1 mod 13. 2 raised to power 1 is 2. 2 square is 4, 2 cube is 8, 2 raised to power 4 is 3, modulo 13. And so on, you compute that everything is appearing except 0, right? 0 is not there anyway in ZP star, right? So all the elements are there. So 2 is a primitive element. Okay. In fact, the element 2 raised power I is a primitive element if and only if GCD of I comma 12 is 1. This you may observe by looking at the table, right? So now that means when this GCD is 1, when I is equal to 1, 5, 7 or 11. So I know in that case the primitive elements modulo 13 are 2, 6, 7 and 11 because you can find all of them, right? And this condition is there. Suppose P is a prime greater than 2, alpha is a member in ZP star. What is ZP star again? Elements which has GCD 1 with P, right? Then alpha is a primitive element modulo P if and only if alpha raised power P minus 1 divided by Q is not multiple of 1 mod P. Okay, it's not congruent to 1 mod P. For all prime Q such that Q is not dividing P minus 1. Again, the proof is there, and I mean, it is there on the slide also, but I am not going to look at it, I guess, right? I'll leave it for you to look at it. Now I think we can, so this was all some basic preliminaries for about your so now we are ready with RSA crypto system actually. So P and Q are large numbers. N is a product of P and Q. Y of N is P minus 1, Q minus 1. And again, I am challenging those competitive programming lovers that can you write a program for factoring an integer? So integer could be 200 digit long, 400 digit long. Think how can you write a program for factoring integer, right? So you must be knowing the RSA, challenge. Okay. How many of you know about the RSA challenge? Nobody. Beautiful, right? So look at these numbers here. If you are not able to view it, you can look at your mobile also, no problem. So you see that RSA 100 decimal digit, and there are prices, but of course it has been discontinued now. $1,000 was one in 1991, 4,429. So some of them I can show you as a sample. So this one is the easiest one, right? This is RSA 100 number. You have to write a program to factor it into, these are two prime numbers, okay? These are two prime numbers. RSA 110, these are two factorization. RSA 120, these are two factorizations. So, all these are known, so for no price was given for these. And I think you see the latest is RSA 250. So 250 digit long number, which was factored in February 28, 2022 at the time of COVID by these many people, right? So the factorization is certainly known. This is the number. These are two prime numbers. Factorization, right? So then what is next? So these are the prices which you can actually look at it, right? It's still, but now this price has been discontinued. $75,000 you can get if you can factor that. $100,000 if you can factor that. So, so number here you can look at it. This is 270 digit long. So this is the number which you should be able to factor. Now you use all your competitive programming techniques and see if you can factor this. You will get, reward. Forget about reward. If you factor, you will be famous anyway, right? So can you factor it? Simple. Problem is integer is given. You have to find the corresponding to prime factors. Can you write a program to do that? Right? So I hope some of you may try and you may be able to do something. Okay. So these are the numbers which are still they have not been factored till now. Even this one has $200,000. So anyone can tell that why they have discontinued the price, because now quantum computer is on the corner, right? And quantum computer somebody may factor, because of course that IBM is having 400 qubits, but still people are saying that it will take another 5 to 10 years before we'll be able to factor even with the quantum computers. So we are safe. That's why all business is going on with RSA system. It's still in the place, right? But Chinese people are doing something. They are claiming that they have done something. I am not sure what they are doing, but that is the thing. Okay. So essentially RSA crypto system, because this is very difficult, and why RSA company started this challenge, just to invite people to approach, I mean, try to back the system, right? And if you can factor, means the things are done, right? So you will see that I'm going to cover some of the algorithms, even some attacks on the RSA crypto system, how they approached initially. But what is important is also you need to look at the complexity of this system, right? What is the complexity of RSA crypto system at different place? Anyway, so I'm just recalling what you know. P and Q are large primes. N is a product of these two primes. So that means phi of n is p minus 1, q minus 1, obviously, because phi is a multiplicity function. So phi of p into q is phi of p into phi of q. Phi of p is p minus 1, phi of q is q minus 1. Our plain text and ciphertext are coming from integer modulo n only. So we are looking at these numbers. So crypto system is NPQAB such that A into B is congruent to 1 mod phi of n. Okay, that is the whole thing. So basically, so this actually the key space basically is okay. It's like encryption rule is what? EK of x is x raised to power b mod n. Okay, and decryption rule is dk of y is y raised to power a mod n. X and y are integers anyway. So there are two kind of keys: public key n comma b is a public key, and pqa is a private key. So the whole key component is divided into two kind of keys: public key and private key. Okay, so public key is of course publicly available, and private key is pqa. Okay, so this is the whole thing, and actually I hope so you know the encryption and decryption rule. So encryption and decryption rules are basically they are kind of working, so you can check that. So how these processes work: since a into b is congruent to 1 mod phi of n, we can write down a into b is equal to some multiple of phi n plus 1, right? Because that's how we are dividing, right? For some t. Now suppose x is a member in Zn star, then I can compute x raised to power b raised to power a, and that value will be, I can plug in the values of product a into b. It turns out to be x raised to power t times phi of n plus 1 mod n, which is nothing but x raised to power phi n raised to power t times x. One factor I can take outside because there is x. This whole thing is nothing but the same thing, modulo n. But we know that x raised to power phi n is what? X raised to power phi n is 1, right? So because x is an element in Zn star, right? So that means this whole value is x mod n. Similarly, you can compute and show that x raised to power b raised to power a. So that means this whole thing is x mod n. Okay. Similarly, the opposite way actually. So as an example, if P is 101, Q is 113, N is, that means N is 11413, phi of N is 11200. Okay. So integer b can be an exponent if and only b is not divisible by 257. So basically GCD of I n comma b is 1. Again, using algorithm 6.3, you can find b inverse if b is this number. Okay. B inverse is this, which is A. Plain text suppose is 9726. Plain text raised to power this is a ciphertext 5761. This is the encryption, right? And so on. Actually, I am anyway. So this is all implemented. I'm it's forget about these lines. Actually, these are there. While writing, I was not having much practice, but anyway. So the algorithm is generate two large primes P and Q. P is not equal to Q. Compute the product in n, and phi of n is obviously P minus 1, Q minus 1. Choose a random B, which is less than phi of n, such that GCD of B and phi of n is 1. Then, you basically you find out these numbers, basically, n, B, P, Q, A. So then you know what is the private key and what is the public key, right? So basically, important thing is about the complexity, because I'm just skipping few of things because you know already from discrete math class. So if you have not done it, you can always revise it. So if x and y are positive integers, number of bits in x is suppose k and number of bits in y is L. Assume k is at least L. Then x plus y can be done in order of k. X minus y can be done in order of k. This big O notation also you know, right? Can anyone tell me what is the big O notation? F of n is big O of g of n if what happens? सब भूल गए हो ना discrete math में, right? So I'm just recalling. F of n is big O of g of n if a function f is a big O of, ये सब पूछते नहीं है एग्जाम इंटरव्यू में, जॉब इंटरव्यू में. मैं होगा तो जरूर पूछूंगा, right? What is f? F is big O of g. So a function f, I am assuming f and g are positive functions, or otherwise you can say that if function f of x is big O of g of x if mod of f of x is less than or equal to k times mod of g of x, where k is known as Borel constant. If you recall, this is big O notation. डिस्क्रीट मैथ में कितने नंबर आए थे तुम लोगों के? तो कुछ भी याद नहीं है, राइट? So the complexity is very very important. Anyway, ठीक है, तो बहुत अच्छी बात है. If you don't know, it's very good. So I have another option for you. Take it as a T problem, and I'm going to ask thinking, right? So that way you will recall. So it will force you to sit down, right, and find out the complexity things, right? So subtraction and summation can be done in the same order. Product can be done in order of KL. This division can be done in order of K minus L, and GCD in order of K cube, right? Also, in Zn, for doing certain operations, the complexities are listed here. These are very, very beautiful complexities. So we need to actually, you want a proof of it. So I am assuming from your design and analysis of algorithm course and some portion of discrete math, you know about these things, right? If not, take a cup of tea and try to prove it. What is the complexity? You compute it, right? So I'm assuming all these things. Bas, isse zyada nahi. So that you have some time. So basically you have time till your holy break, right? Do verify these complexities. I am going to ask you, I am telling you. In someday you will see there is suddenly a quiz, and I ask you to prove that the complexity of these, say m1 raised to power inverse is order of k cube, right? Okay. So that's all.